out of the gel coat. We went through the whole lamination process. Now we're over on the deck side where the upper half of the boat is actually laminated. The process is that we start through on top of the gel coat, putting a skin coat, we call it. That builds a barrier between the gel coat and eventually what will become the mass of the laminate. We have a term we call zone tempering. That really starts to take form here because not all areas of the deck need to be built the same. When we say zone tempering, we're talking about building different areas to a different specification because there are going to be different requirements, different stresses on it eventually when the boat is in use. We've used finite element analysis to confirm what real world testing has already revealed to us, and it gives us an idea of where these stresses are under certain loads. In doing that, we're able to put the exact amount of fiberglass, the right kind of laminate, in the right direction, in the right areas. And as the deck goes through this process, we're starting adding layer upon layer until we get the general laminate where we want it. Then we'll move over and start putting stiffeners in. As you see on this one, some pultrusion has already been added, and that is going to be deeply embedded into the laminate in areas such as the seat base and places like that. This boat's moving down the line now where it's going to get more laminate applied. We'll look at it in just a moment. You see a lot of things that have been added on as this deck has gone through the lamination process. We started out with that skin coat to build the barrier, and we strategically placed different materials to bear the loads that we know that will be applied to this boat eventually. So whether it's a live well or a closed cavity bag molding, it's used for a storage or a rod storage liner, so many other components that are being built up in the other part of the plant as this deck is coming through the line. It's delivered just in time and fiberglass to the deck while it's coming through this serpentine production circle. Why that's important is that in this upside down position, it gives us an excellent opportunity to fiberglass all the way around the perimeter of those boxes. And what that does is ensure the dryness of them and eventually satisfaction to the customer. One of the things that we really pay a lot of attention to is that we want to make sure that anywhere a screw or a bolt or a piece of hardware is bolted onto the deck eventually, we want to make sure that that has the proper backing so that it will stay in place. And we use our pultrusion process to build a lot of the backup that we see in various places on the boat. You saw on the pultrusion and how it was really invented for the transom. We use it here and perhaps for a different reason. I like to show you really what that means when you have that kind of backing on the back side of the deck. We looked at a lot of these parts, pultruded pieces on the deck that we just saw being laminated, but I wanted to show you in a little more detail. This material, as we explained, was developed for transoms over on the hull side. This material is unique to Ranger. It's built in-house, and it's a material that's pound for pound is stronger than steel. One of the attributes of it is it has a real high glass content, very little resin. When you get high glass and low resin content, you have a strong laminate and you have one that's very lightweight. We use this for backing of screws, trolling motors, cleats, and so forth. And I think I can show you in a little illustration really why that's good in the finished product and what that means to a Ranger boat. There's several different materials, and we're not picking on any one. The one that has the best screw retention, I believe, is this one, so we're going to take the best of the best and we're going to compare it to pultrusion. Screw retention is important because we want it to hold. When you're out in the elements and your cleat is screwed through from the top, or the handles or the hinges on the lids or whatever, it's important that they stay in place and not back out or not strip. I'm going to screw this little handle onto this piece of material that's typically used for backup. Take a stainless steel screw and we'll put a couple of screws in it, see if we can get it to, I'll be real careful not to strip them. I'm going to go down easy but get it tight. There we go. Put another screw in. And we'll put a third one in just to make sure that we're getting everything we need, everything possible. We've welded up this little handle, and you can see that that went into that material that's almost the same thickness as the pultrusion material that we typically use. So you can see with a little bit of leverage on this screw, it pops right off. It did, I guess, all it was expected to do, but the end result is not adequate. Now let me take this same material and we'll back these screws out of the hole. And I'm going to have to drill a pilot hole in the pultrusion material because it's so dense that you can't drive a screw through it without doing that. So I'm going to drill a couple of pilot holes. We'll get one here, and you can see the fiberglass dust. Let's see if we can line it up and get another one. Now screw our part down onto that. I'll need to be more careful with this because I can actually snap that screw in two. Okay, so I've got a couple screws. I'm not going to put 3 in this because there's absolutely no need of it. And as you can see, no matter how hard you try, you can't pull that screw out. The reason we do all this and the reason I want to show you is because we want you to have the confidence that what's below the surface, what you can't see necessarily in the showroom, is just as important. There's been just as much or more attention to detail given to that component as there has the surface that you're accustomed to seeing in a shiny, glossy finish. You've seen the laminating process and hopefully have an understanding of how we built the deck and got it to this point. But this is a real interesting operation because we're actually removing this deck out of its mold. Remember the small scale model that we looked at and saw how the mold is upside down and then a boat is being built in that position? Well, here we're raising it up out of its mold where it was laminated, and this apparatus is to stiffen the entire deck so that we don't put any undue stresses on that deck until we can get it turned over and eventually lowered onto its hull that it will be mated with. When the deck or big part is removed from the mold, we move it into this area of where we do the cutting. The cutting machine we're looking at is something that we developed a few years ago from our experience with actually cutting the pultruded material, which was very, very difficult to maintain equipment when you're cutting something that tough. We took it a step further here and we have a 7-axis robot that uses water to cut the fiberglass. When we move this deck into position and jig it up within a very close tolerance, then the machine is going around and doing its search now, looking for the accessory pack, the group, the standard equipment, actually going through a dry run of what it's going to be cutting. This system cuts with a very fine stream of water. It's a very small orifice at the machine head, but it's very effective, and it will cut fiberglass up to, well, very thick, and even without abrasive. We're just using straight water in this application, compressed to over 50,000 PSI. It's a very effective way to cut fiberglass, and it's unique to the Ranger plan.